Hello friends, so today's topic is fugacity. So fugacity is not very different from pressures. Okay, it is a sort of fictitious pressure. So now let's analyze fugacity for ideal gases and real gases. Okay, for ideal gases fugacity is equal to pressure, but for real gases fugacity is equal to fugacity coefficient and pressure. Why? This is because the pressure exerted by a real gas is different than that from ideal gases. Okay, because in real gases there are molecular attractions, but this is not true for ideal gases. Now we all know that the equation of free energy is given by this equation. dg is equal to vdp minus s dt. We all know that. Now we are not going to discuss why dc is equal to vdp minus s dt. We all know that. Okay. At constant temperature, this term dt will be equal to 0, so this whole term is equal to 0. So then dg will be equal to vdp. Okay. now chemical potential. Here chemical potential is defined as dg upon dn. For 1 mole of a gas, this term will be equal to 1. So chemical potential will be equal to Gibbs free energy. Okay, so we can put d mu instead of dg. d mu is equal to vdp. Okay, now we are going to integrate between suitable limits. Okay, this mu I naught, this is the chemical potential of standard state, and this is mu I. d mu is equal to p naught to p, this is the pressure of standard state, vdp, and this is equal to delta mu is equal to, okay, for 1 mole of a gas pv is equal to RT, so v will be equal to RT by p. So we can put p naught to p RT dp by p. Okay, so this is going to be equal to RT ln p by p naught. Okay, so mu is equal to, delta mu is equal to RT ln p by p naught. So this is the equation for pressure. Now we can express this equation in terms of fugacity. So we discussed that fugacity is equal to fugacity coefficient multiplied by pressure. So pressure is equal to fugacity by fugacity coefficient. So here we can put delta mu is equal to RT ln p f. Okay, for this is p. Okay, so this is equal to f by phi by f naught, because this is p naught by phi. So phi is cancelled out, and this is what remains, RT ln f by f naught. This is the equation in terms of fugacity. Now we have to learn what is the physical significance of fugacity. Now the physical significance of fugacity coefficient. So for ideal, fugacity is equal to pressure. Okay, fugacity is equal to phi p. So if fugacity is equal to pressure, then this coefficient must be equal to 1. Okay, f is equal to p, so phi is equal to 1, this coefficient is equal to 1. So for ideal gases the fugacity coefficient is equal to 1, and for non-ideal this fugacity coefficient is equal to f by p. So from this we have come to know that closer the value of fugacity coefficient to 1, the more ideal solution. Okay, I'm writing here, the closer the value of phi to 1, the more ideal is the gas. So this is the physical significance of Fugacity coefficient. That was the significance of Fugacity coefficient. Now what is the significance of Fugacity? So the significance of Fugacity is, so we have considered a container in which we have some liquid, okay, and from this liquid some of the molecules has escaped its liquid state to vapor state, okay. So and vice versa, from vapor some of the molecule has escaped its state to liquid, okay. So this escaping tendency is called Fugacity, okay. So this is the physical significance of Fugacity.